Okay, so far we've had things that are pretty easy. We can use the Pythagorean theorem. But if we're going to add vectors that are not perpendicular, you don't have a right angle, obviously we cannot use the Pythagorean theorem. Now, I do have people saying, well, let's use the law of sines or cosines, and you can. It works fine. But honestly, I think it's easier just to do it the method I'm going to show you. And also there might be some additional questions, so I guess I would just do it the way that I'm going to show you. Okay, so let's do the first one, and I'll try to draw some good pictures here, and you try to draw some good pictures that are to scale, and they have the right angle and that kind of stuff. So I'm going to have a plane that flies 25-degree angle to the ground. Now I know I'm making this 25-degree angle a little large, but I think it's going to be helpful to see it a little bit better. So the plane goes for 137, that should be kilometers, not meters, kilometers. And then it changes direction and actually goes 10 degrees to the ground. So I'm just going to, continue this ground thing, and I'm actually going to narrow out the plane a little bit to only go at a 10-degree angle to the ground, to the horizontal. Okay, it doesn't say an additional 10, it just says 10 to the ground. So I'm going to just do the ground, and then that's my one angle, or my one vector, and here's my other vector. I should have drawn that a little less long, so I'm going to try to do that. Actually, go back. I'm going to try to draw that to scale, 90 kilometers. And then the question is, well, what's the total altitude at this point? So I'm going to draw in the resultant vector. The altitude, of course, would be this y part here, the altitude. The distance or displacement would be our x. And then we could also do an angle. Look, I'm out of colors, so I'll do an angle there too. So I know they didn't ask for all of this, but we're going to go through and do it all anyway. All right, so the first thing that I would do here is I'm going to take each vector, okay, and do separate things to it. I'm going to take this 137, I'm going to break it up into its y and x. Okay, I said that backwards, but into its x and into its y. Okay, I'm going to break it up, resolve those vectors. In the same sense, I'm going to break up this one into its x and its y. Now what that does for me is basically to show me what everything breaks down to in a north-south, east-west direction type thing. And then I can add them. Now these all appear, they're all positive. I could have a picture where something goes east for a while, then it goes west for a while, and so I would subtract those. So basically what this does for me is it allows me to see the resultant vector as simply components of the vectors that made it up. So here what I have is, if I can figure out this right here, okay, and then I can come up here and figure this right here, I basically have this whole entire x, because I'll have this part of x from here, and I'll have this part of x from right here. So basically I do that math-wise by doing the cosine of 25 times 137. So if you need to work that out with the Pythagorean theorem and SOHCAHTOA, go ahead. But this is going to be the cosine of 25 times 137. In the same sense, because this is adjacent, this is going to be the cosine of 10 times 90. As far as the y's go, I will find this and this, and it will be, if I add those, the total y, the altitude. And mathematically to do this, I'm going to find the sine of 25 times 137. In the same sense over here, this will be the sine of 10 times 90. And when I get those, I'll add them up, and that will be my total y. Okay. Now, you'll have to go through and probably calculate yourself what's going on here, but when I go cosine of 25 times 137, I get 124. When I do cosine of 10 times 90, I get 88.6. Okay, so I'm moving this vector parallel down here. This is also 88.6. So I have a total x direction of 124 plus 88.6. Got a total x of 212 kilometers. As far as y goes, I have the sine of 25 times 137 is 57.9. And the sine of 10 times 90 is 15.6. So together, this y is going to equal the two combined, which is 73.5 kilometers. Okay, so take a minute to understand where those came from the picture, and realize now that the resultant is going to be the square root of 212 squared plus 73.5 squared. So the resultant vector here is going to be 225 kilometers. Now I didn't answer the question, the total altitude, but the total altitude is going to be 73.5 kilometers. That's how high up it is right now. But if I wanted to go through and do the resultant, I could do that and find that it's 225 kilometers. The other thing I might want to do is, well, actually I have to do it, is to talk about that angle, describe that angle. And so, again, be careful, draw these pictures correctly, because you might, if you draw it small enough or more confusing, you might think it's a 25-degree angle, but that was the one vector, not our resultant. So our resultant vector, the angle, is going to be the tangent of theta is equal to the 73.5 over the 212. So our angle turns out to be 19 degrees. And it'd be 19 degrees above the horizon, I guess, would be good. You could also do it this many 19 degrees north of east, the way that I drew it. Okay, let's do one more in this sequence. Let's say that we have a hiker that walks 35 degrees south of east for 25.5 kilometers one day. So what I'm trying to do here is a 35-degree angle, and they walk 25.5 kilometers. Then the next day they turn, oh, and I just realized this picture is going to be a little off, but that's all right. 65 degrees north of east, so this is east over here, so north of east, and they travel 41 kilometers. And the question is, what is the resultant vector? And I probably want to describe that angle right there, because it'll just be convenient to say this many degrees north of directly east. Okay, so that'll be the angle I want to use. All right, so as I do this, you want to go back and you want to just break up each of these vectors into their individual vectors. So I'm going to break that one up, and then I'm going to break this one up. Okay, and that's kind of messy, but I guess we're going to go with it. Okay. And when I break those up, again, can just use SOHCAHTOA to find out those values. Okay, so this is a 35-degree angle. And so basically this is a 35-degree angle. So this is a 55-degree angle, okay, 65. Okay, so to break this up, I can see that this is going to be, again, you have to work that out yourself, the cosine of 55 times 25.5. And this right here is going to be the sine of 55 times 25.5. In the same sense over here, this will be the cosine of 65, because it's adjacent, times 41. And this is going to be the sine of 65 times 41. Now you may want to take a minute just to realize with SOHCAHTOA, you know, I could have done, instead of this one being the sine of 55, I could have done the cosine of 35. Okay, but just make sure you're drawing clear pictures and you're using the right SOHCAHTOA. Okay, so those values are basically going to end up being, let's see, got the cosine, all those units. This is going to be 20.9. And this one is going to be 14.6. This one over here is going to be 38.2. And this one is going to, no, I'm sorry, that's the addition of it. This is going to be 17.3. And this is going to be 37.2. Okay, so now when you add these up to get your resultant vector, you want to get your total eastern direction, eastern, and total northern. Now notice with the eastern they add. I'm going to add this one and this one to come up with a grand total going east of 38.2. Now, with this part right here, you're going to see we've gone 37.2 north, but we've gone 14.6 south. So we're going to actually subtract those. I'm going to take 37 minus the 14.6, this right here, which is, okay. I'm done now.